All right. Anyway, yeah. Yeah, we're speaking. So last time we did some upper bounds for using uh, randomness. Well, I mean, that is greater than quite a few of them, right? So, I mean, the main thing was greater than, and which used equality as a subroutine. And if you remember, so I sort of talked about the public coin model, uh, public coin and private coin, right? And as I said, the public coin model seems like a bit too much in the sense that at first sight, with the definition, it seems a bit too liberal. But well, we just showed that you can anyway, assume it's public coin because for private coin, you generally speaking, add log n. Yeah. If you remember, there were like two components. So, like what I showed was our private coin epsilon of, let me just, of f. This was our public coin epsilon of f plus order log of n. Sorry, there was a delta here, right? Plus I keep forgetting, was it log over? Log over. Yeah, 1 over delta, but was it log or? Yeah, there was a log. Or was it there a log or just 1 over delta? No, there was a log. Yeah, there is. Yeah, Chernoff applies the law. Yeah. Yeah. So there was a log 1 over delta. Now, notice that, there's also actually some sort of a, yeah. So, I mean, for most applications, this would be like good when we are just talking about epsilon and delta being constant, right? But there would be situations we would just soon see, yeah, where if sometimes this epsilon and delta need not be a constant, and we will come to these cases. Yeah, I mean very soon we're going to introduce a method where these things will come up. Then you have to be more careful. But for like when you're talking about usual 1/3, 1/10, 100, 1000, whatever kind of constant error, then basically an order log of an additive cost is all that you care. That all that results. So you might as well consider public coin. Yeah, it doesn't matter. Um, and what the one of the reasons for showing this greater than protocol was that public coin allowed us to think of it very naturally, right? So all I did was a public coin protocol, but now you can just convert it into a private coin protocol by just applying this hammer, right? And you just get an extra order log n. Anyway, the cost was order log n. So all in all, private coin is also order log n, right? We saw an order log n public coin protocol for greater than. Order log n times log of n was easy. To shave off that extra log of n, one had to be extra careful, and yeah, and we could shave it off, and then we got it down to order log n. So I'm just saying now with private coin you add another order log n, so it stays order log. Yeah. Okay. So this is good to know. Right. So now, and we saw that for private coin, log the approximate rank was a lower bound. Yeah. I showed you maybe a couple of classes ago. Yeah. So yeah. So okay. But then log the approximate rank was a lower bound on the private coin protocol. But because of this just an additive log of n, minus to that minus a log of n is also a lower bound on the public coin, right? So if you are talking about the high regime of lower bounds, log approximate rank is a lower bound even on the public coin because of this ham, right? Okay. All right. So now today what we're going to do is basically get back to lower bounds, right? Which is how do you prove lower bounds? How do you prove lower bounds. And I will now assume that, okay, as I said, if I from now on, if I do not put a superscript, yeah, I will be anyway sloppy. But if I do not put a superscript on this R, assume it's public coil. Okay. Okay. Most of the time when we are trying to prove lower bounds, the lower bounds will be much stronger than log of n, so it anyway doesn't matter. Yeah, public or private. Yeah. So this is our question. Yeah. And as in any randomized complexity, when you try to prove lower bounds, yeah, you have to go to Yao. Yeah, I mean, this is basically the basic principle of proving lower bounds is because of Yao, which is, I mean, it's very simple, but it's like a beautiful principle. I mean, called in many ways, in many different fields, Yao's min-max principle. Yeah, that would be our starting point as well. Yeah. And those of you who have taken a query complexity course on me has last semester, I'll again do it. The proof remains identical here because again, this Yao's min-max principle is very broad. It can be used in many different settings in all sorts of zero-sum games and so on. But here I will, just to make it very self-contained, I will show you using linear programming duality, which is anyway needed, without which I don't know if you can prove it otherwise. Yeah, there is some hyperplane separation. Yeah. So yeah, but I'll show it again. One side of it is easy. So this min-max principle. Let me show the easy side, and from after I show the easy side, we'll put a definition in place, which will naturally arise from the easy side, and then we'll show the hard side as well. Okay. So if you have been given, suppose, yeah, and notice this the fact that this is a protocol is not going to be so important here, right? It's going to be any strategy or anything is equally good. So just check it. I'll continue saying it as a protocol because instead of a randomized protocol, you can think of a randomized strategy. Yeah, it doesn't matter, but. So just for context, I'll continue to say it as a protocol. So suppose pi is a randomized protocol. Yeah. Solving f of some cost. Yeah, solving f. Yeah, with some cost. Let's say with cost c. Yeah, and right. So now, by its very definition, it means that for all possible inputs, inputs to a protocol are of this form, but to a decision tree, it could be in another form. In any other game, it could be some other form, right? So, but here, let's say, oh, sorry, I just jumped one step ahead. Yeah. So for every xy, yeah, in the input domain, so there's a table on which the inputs are on one side. Yeah. So you take any input from there. For every possible input xy, we know that there is this mixed strategy or a protocol, depending on what context you are in, that says that probability over the internal coin tosses of the protocol of the strategy, pi of xy is equal to f of xy is always at least 1 minus epsilon. Right? So an epsilon error proof. This is true for every xy. So in particular, for any distribution, mu over our inputs, yeah, we also have this, right? Probability R, probability mu xy according to mu. Yeah, the R is the sorry, this is not pi xy, but pi xy R. I'm sorry. I'm going to write it this way, xy R. Yeah. Because pi needs to have its internal coin toss given, right? So now this probability xy according to sample from according to mu and the probability of the internal coin toss is this is still the same, right? Oh, yeah. Yeah, I haven't done anything, and the easy side is basically doing nothing. Yeah. So now I can just sort of interchange these things, right? And therefore, I know that probability over R and probability over XY, because these are completely independent, right? I mean, we're choosing completely independently. Yeah, so pi x y r, these two distributions are independent, that's what I meant. Yeah, is greater than or equal to 1 minus epsilon. Yeah. And now it's clear that if the probability over, if I just look at this quantity, if this is going to be greater than or equal to 1 minus epsilon, right? This probability is going to be greater than, this quantity is going to be greater than or equal to 1 minus epsilon. As you vary r, there is an r for which this inside thing, for that fixed r, it must be at least 1 minus epsilon, right? So there exists therefore a fixed r, for which fixed r0 says that probability over xy okay. So this just follows by just playing around with it. Yeah. So not notice that once I fix R0, then of course pi is no longer a randomized protocol. For every fixing, it gives rise to a pure deterministic or pure strategy, right? Protocol, which agrees with f of xy over the distribution. Now, at least 1 minus epsilon. Now, this choice of R0, of course, depends on mu, right? If you take a different mu, you might have to fix the randomness to something else. But for every distribution mu, non-uniformly, there is a choice. Yeah, and therefore you know this choice so that you can fix it and get a pure deterministic protocol, so that that deterministic protocol now errs at most 1 minus epsilon. Right? So this is now a deterministic protocol. I can just say that, sort of, I can move this, this R0 to over here, because it's hardware. Yeah, so that's a deterministic protocol. Yeah. Now suppose, therefore, one possibility of proving a lower bound is to find this sort of a hard distribution mu, such that every deterministic protocol of small cost. So, remember, this was the worst case, our cost was worst case cost. So for every choice of randomness, the deterministic protocol will have cost at most C, where C was the cost of the randomized protocol, right? So if I could find a distribution such that for that distribution, every deterministic protocol of cost less than C would err more than epsilon, then I would be done. Right? Then I would have proven a randomized lower bound just because of this easy side, right? Because this would show that there is no fixing of coin tosses for which this could occur, and this would violate what I just said, right? So this gives me a strategy which basically sort of seems to say, from lower bounds against deterministic protocol, which psychologically makes us very happy, right? Why does it make us very happy? Because, again, if it's a deterministic protocol, the leaves are beautiful, pure rectangles. The deterministic protocol is partitioning, it's partitioning its input space into pure rectangles, just as any deterministic protocol has to do, into 2 to the C rectangles, right? And so we can go back to our analysis of rectangles, right? And hope to prove a lower bound by choosing a hard distribution mean. Okay? Yeah, but this is now against erring deterministic protocol. Now, this is not quite the same, but which this is going to be a huge problem in some sense, or one has this is where randomized protocols and pure deterministic zero error protocols will differ, right? So we have to analyze deterministic protocol, but they can err, right? So the leaves of a deterministic protocol, of such a deterministic protocol, need not be a monochromatic rectangle. They would be rectangle, but not monochromatic. So just by analyzing pure monochromatic rectangles, we were getting away in deterministic protocols. That avenue seems to be gone, right? So we have to start analyzing rectangles that are sort of getting corrupted by some errors, right? Okay, so we'll learn how to deal with it. Now, before we proceed, we would like to understand, I mean, I haven't still sort of formalized it, and I'm going to do it in a moment, but, I just said, okay, so if I can find a hard distribution, so what have I said? I've said, finding a hard distribution against cost C deterministic protocols is an R. Yeah. So just let us
Again, slightly erring.
distribution against cost C erring deterministic protocols. Yeah. I mean, this is always there within brackets. Yeah. Yeah. So now let's formalize this a little bit, and then I can say the next thing that I want to say. Is like, let's define this notion d mu epsilon of f. Yeah. So f is any function. D mu epsilon. So mu is any distribution. So epsilon is greater than 0 or greater than equal to 0. Yeah. And, typically is less than half. Yeah, this is the error. Mu is a distribution. Yeah, over 0, 1 to the n cross 0, 1 to the n, or in general over your input space, which is in my case 0, 1 to the n cross 0, 1 to the n. Yeah, so it's some arbitrary distribution, and now I want to understand d mu epsilon of f. I want to define this. So what is this? This is basically the cost. Yeah, is sorry. This is less than equal to C, yeah, if there exists a cost C deterministic protocol phi such that exactly what we derived from right? If xy is sampled according to mu, phi of xy is equal to f of xy with probability, or is not equal to f of xy, whatever. Probability at most epsilon. Yeah. So I want to minimize this C. So d mu epsilon of is less than or equal to C. So it's equal to the smallest number C for which this happens. Yeah. So is this clear? So now I can talk of, so this is, I am using this D as is the convention, just as we use D for deterministic complexity. But this is often called the mu epsilon distributional complexity of F. Yeah. So what we have proven, the easy side of Yao, what we saw was that for every mu, yeah, R epsilon of F is at least D mu epsilon of F, right? And therefore, we could, if I wanted to get the largest possible bound, what I should be doing is that, let me call it D epsilon of F to be maximized over mu, D mu epsilon of F, right? I choose the hardest possible distribution that I can get, right? And so what I know therefore is R epsilon of F is in fact greater than equal to D epsilon of F, right? So far, just and now, just whenever we we develop a technique, and why is this useful, you will see in a moment, but maybe it will work sometimes, And you will see it often works. But the question is, does it work always in principle? It's always important to understand, how are these, it's greater than equal to, but is it like, can R epsilon of f be much larger than d epsilon of f? Yeah, or there is always going to be some distribution mu which will witness this, right? And it turns out that this is exactly equal to this. These are two things, just being said differently. Exactly equal, right? There's not even like a theta there. Yeah. Okay. Yeah, so this is very nice when this happens, because this quantity seems a little different, whereas the quantity on the left seems completely different. There's no, here on the right there's no randomness over this thing, right? And you should not be completely surprised if you haven't seen this before. Why should they be related? Yeah, it's simply because of, when we sort of did this implicitly, what I've been using when I'm in public coin is that, after all, a randomized protocol is a distribution over deterministic protocols, right? Essentially, a randomized strategy is when you are giving me a randomized protocol of cost C, every randomized protocol of cost C does the following. It lines up all the cost C deterministic protocols that there are, right? In fact, this is a finite collection of objects, yeah, because we are talking about cost C, and the input space is finite, yeah, and then it decides on a particular distribution. With a certain distribution, it's sampling a deterministic protocol and deciding to let me run it without even looking at the input, right? It's independently sampling this and it's running it and hoping to give a right answer, right? So that's exactly what's going on. So therefore, if I'm saying this equality, yeah, what is this saying? This is saying that therefore there must exist, suppose you told me for every distribution mu, there is a best strategy, right? So therefore, in some sense, if this equality has to hold, there's some distribution over these best strategies that the adversary is going to, that the algorithm is going to play, and then hope that he's doing fine, right? This, in fact, always happens. Let's prove this. This one is the hard side, and this is the hard side. Yeah, because you need to do this dual. Take the dual. The dual of a linear program, such a simple object, is always, like a magical object, right? Once you take the dual, it just tells you things in a different way. And often it's very hard to prove that these two things are the same. Again, there's one side, the guarding side is always easy, which is exactly what I did in some sense. Yeah, the other side, where there's, there you have to use convexity, and that's what we are going to do here. Yeah. Okay. So how do we prove the fact that these are equal? Well, let's again, if you have to formulate the right linear program, and let's try to do this linear program. I mean, what I think the right thing to do, the natural thing to do here is, because I said R epsilon of f is a distribution over deterministic protocols. So let me try to write down a linear program describing this. Yeah, this condition that you have to make error epsilon. Yeah, so you have to your success probability has to be at least 1 minus epsilon. So let me line up all the protocols of cost C. Yeah. So somebody has asserted R epsilon of f is less than equal to C. What does this mean? Let's write a linear program, right? If I want to write a linear program, the dumbest way to do is I'm going to look at all possible inputs, right? So let's say the input, and I'm going to here make each z I would be some pair of x, y, but I'm going to be writing it as z in terms of z. So z1 to z capital N, yeah, where capital N, this works for every possible setting. So I'm being as general as possible. So z capital N, these are the set of all inputs that the randomized algorithm would be subjected. Yeah, this is the set of inputs. This is the set of all possible inputs. Yeah, and now let's look at pi 1 to pi s, yeah, the set of all deterministic protocols of cost at most c. Yeah, I just like that one. Okay. Now, well, we want to say that, I mean, these are all protocols of cost c. So therefore, there is some strategy, yeah, so that the error is smaller than epsilon, or the success probability is larger, right? So I want to maximize my success probability by choosing my distribution, right? Okay. So if my success probability is let's say p, so I want to do maximized p, yeah, and what am I subjecting it to? So for every input, sorry, for every, why is this happening? Yeah. For every j in n, so I'm indexing all possible inputs, right? Well, I want the probability of correctness being to be larger than p. So that means, I want what's this? Okay, so now let me define another variable. Let me call it the aij.
So what is P supposed to be?
P is going to be my success probability. Okay, in the worst case for every possible input, right? Yeah, 1 minus epsilon, exactly. So P is like, P would be exactly equal to 1 minus epsilon. Yeah. So now aij will be equal to 1 if and only if pi I, sorry, let me just be careful here. Yeah, pi I of zj is equal to f of zj. So if I run the ith protocol and the jth input, it gives me the right answer according to this function f. Yeah. So now it's just that, right? So I want to sum up aij. Yeah, and let's say gamma j is the gamma I is the probability that I'll run the protocol I, right? So I equals 1 to n, yeah, minus p, minus p,
Greater than I.
no,
S.
this is greater than equal to p. So this should be
Greater than equal to 0.
greater than equal to 0. So I want to just write it in this other way. Let me just be, yeah, so let me just say, okay, p minus this would be less than equal to 0. Yeah, I want to write the linear program the canonical way. It's a maximization problem.
Right?
Huh?
Summation, are you going from 1 to?
Oh, yeah, you're right. Here, right?
Right.
Yeah. Yeah, so I'm just writing it in this way so that, I write it in the canonical way, right? I'm maximizing something. So my constraints should all be in this form. Yeah. Okay, so this is just that acceptance problem. So, I want to maximize P. Well, now also this gamma I is the probability, so it's a probability distribution. So I want to say summation gamma I equals 1 to S should be less than equal to 1. Yeah, well, it has to be equal to 1, but you just see it's a maximization problem. So the maximum will always be attained at the corner when it's exactly equal to 1, because if there's a slack, you can move the slack, make it tight, and it only can maximize P. Yeah, because all these gamma i's are greater than equal to 0 for every I. Yeah, so this is exactly the problem that is to be solved if one has to say, I mean, this has a feasible solution. So P, here the maximization of P, when you say that R epsilon of F is at most C, this means that this program has an optimum which is at least 1 minus epsilon. Yeah, I've just translated this into this linear programming language, right? Okay. Yeah, I mean, this is something that most of you have seen, but if you haven't seen this before, it's good to know how these things are proven. Yeah. Now let's look at the dual. Yeah, because I'm just saying that this equality is basically just taking the dual of that. You will get this. Okay. So if you take the quality, the dual, so then this would be a minimization, and I'll just say minimize perhaps epsilon, right? Yeah, and I'm going to multiply this by epsilon. I'm going to multiply this by each of them by mu j, which is going to be the distribution over inputs. Yeah, and let me just write it down. You can check it for all I in what was this? S. No, this is yeah, for all i's. Yeah, for all lengths of the place, and I was this here. And this will be epsilon minus summation j j j is greater than equal to 0, summation mu j equals 1 to n be greater than equal to 1 and mu j. Just check this. This will just yes. So here my multipliers here are mu j. This is epsilon, and I'm minimizing epsilon, and this will you can just taking the dual, you will get this. Okay. Now, what does this say? Now let's just interpret the dual, right? This is saying, well, so you're trying to minimize this epsilon, right? So that means we know by the way this maximum is equal to this minimum, right? This is the linear programming duality giving us, and so it's saying, you want to find this mu j's are just going to be distributions, because again, just as before, the summation of mu j will be exactly equal to 1, because if it's greater than 1, you can just bring it down to 1, and that will only minimize epsilon. So you may assume that. So this is an honest to God distribution on inputs. And then you're saying that, for every one of your protocol, every one of your deterministic protocol, right? That deterministic protocol is going to give me the right answer with probability at most epsilon, right? So you're trying to reduce the success probability as much as you can, right? Yeah, because you're minimizing epsilon. Yeah. Okay. And so therefore, if this P, yeah, is smaller than 1 minus epsilon, right? That means there is a distribution mu where you will find that for every protocol of cost C, yeah, there is a distribution mu which will witness that this minimization, this success probability will go down, yeah, smaller than 1 minus P. Sorry, 1 minus, no, let me just say this is confusing because this is
Too many epsilon.
there are too many epsilon, so let me not call it epsilon here, let me call it A. Sorry. Yeah. Yeah. So the point is, if the success probability can be no more than P, yeah, or by choosing every possible strategy, yeah, then that is what it means, that the cost is larger than C. When I want to say that, suppose I want to say R epsilon of F is strictly bigger than C. That means every cost C protocol, randomized protocol, which is like every protocol is basically a probability distribution over deterministic protocols of cost at most C. Yeah, they will err with probability more than epsilon, strictly more than epsilon. So therefore, their success probability will be less than 1 minus P. So this maximum, sorry, less than 1 minus epsilon. So this is saying that this P here, yeah, this maximum over P can never attain 1 minus epsilon. It will be smaller than 1 minus. Well, then this minimum here is also going to be smaller than 1 minus epsilon because of duality. And now that you will find a distribution, a hard distribution mu, so that every distributional strategy, every deterministic strategy, which is every deterministic protocol of cost at most C, will err with probability more than epsilon. Yeah, it will succeed with probability smaller than 1 minus epsilon. Is this clear? Yeah, because this is exactly what it's saying, right? So here, suppose because I wanted to say that there is always a strategy, there is always a way of doing this, right? So if this is larger than C, then this opt here, so let's call it opt 1. Yeah, so this opt 1, this implies that opt 1 is less than 1 minus epsilon. Yeah. If it was greater than or equal to 1 minus epsilon, then this cannot be greater than C. Right? This is an if and only if. This is greater than C if and only if opt 1 is less than 1 minus epsilon. Yeah. So if this opt 1 is less than 1 minus epsilon, then opt 2 which is equal to opt 2, which must also be less than 1 minus epsilon. But if opt 2 is less than 1 minus epsilon, what does it mean? It means there is a distribution mu, right? Yeah, where the minimum goes below 1 minus epsilon. Yeah, and so therefore, against this distribution, every deterministic protocol of cos C succeeds with probability smaller than 1 minus epsilon. Yeah, so this which just means that d epsilon mu, where the mu is obtained as the solution of f, yeah, is strictly larger than C. Yeah, so therefore, this two opt being equal just shows that this is a complete method. Yeah, in other words, it just shows that R epsilon of f is exactly equal to max. Let me just write it again, mu d epsilon mu of f, which I defined to be d epsilon. Is this clear? This is Gauss principle. Okay. All right. So, yeah, I mean, usually you only use the easy side. This is just to tell you that your pursuit of a hard distribution in principle should always succeed. It is a complete method. Yeah. There have been situations, I know only of a few ones, where this has yielded an algorithm. You sort of somehow argue that for every distribution you give a deterministic protocol, that somehow is easier. And then therefore you conclude that there is a randomized trend. Yeah. In communication complexity, I know of one. At least two things there. Yeah. Talk to me after if you're interested. Yeah, it's sort of very, very bizarre, right? That this is a way of designing, this would be a way of designing algorithms. Yeah, but yeah. Okay. Now, as I said, because we're going to prove lower bounds, I will be mostly now talking about the easier side of okay. So how do we use this principle? So basically, therefore, we have to understand how do we prove. So the question is therefore, boil down to how do we prove lower bounds on d epsilon of f, right? This is the same as r epsilon of f. And therefore, how do we find? Okay, so the first thing there is to, the first thing is to find this mu, the hard distribution. Yeah, but even if you find mu, yeah, how are you going to prove that, how are you going to analyze this erroneous deterministic protocols, right? Yeah. So here is a method called the discrepancy method. Yeah, the method might seem a little strange, but it's actually a very natural. It goes in hindsight. It is a very natural method. This was first used, as far as I know, by Chor and Goldratt. in the 80s, I forget the name. Benny Chor and Oded Goldring. Uh, I think 83. To prove randomized lower bound, I mean, they were doing other things. They were basically eyeing extractors, yeah, randomness extractors, and in which this two source extractors to be sure. But we can talk about connections between communication complexity and two source extractors. Yeah, they wanted to prove that inner product is a good two source extractor. Essentially, it boiled down to proving inner product has small discrepancy and hence large randomized communication. Okay, I'm not going to allude to extractors in this course now. That's when they discovered the discrepancy method. Actually, the discrepancy method, there's a book by Bernard Chazelle called Discrepancy Method. So, it has been used in, there's something called geometric discrepancy. So, discrepancy is a very loaded term used in combinatorics and analysis, it's used in number theory, but it's very similar here as well. Okay, but when I said by Chor and Goldreich, I mean in the context of communication complexity, they were the first ones to sort of define the discrepancy method, and it's a very natural thing if you know what discrepancy is. So, see, we want to show. The name of the game is I find a hard distribution. Let's say even the uniform distribution. You would expect that most hard functions for most functions the uniform distribution would be hard, right? And now the point is these protocols of cos 2 to the c can err. At the least they are no longer monochromatic. So you have to analyze non-monochromatic rectangles. But if you just think about it, here is a protocol. Yeah, and not make a drawing truth. Yeah, and so here's some path, and these are the leaves, and one after the other, it has partitioned. I mean, it's an honest to God partition of its input space, right? It's just that these leaves, which were so nicely monochromatic before, they are no longer monochromatic. Yeah, but you see, most of the leaves or most of the massive leaves must be nearly monochromatic because the protocol cannot make too much error. Imagine I am under the uniform distribution. So every point gets the same mass, weight, right? So just the probability mass is directly proportional to the number of points inside a rectangle. So there are only a few rectangles because the cost, the most of the protocol is small. So the total number of leaves is small, 2 to the c, much smaller than 2 to the 2n, right? Let's say 2 to the root n, for instance. So the average rectangle is enormous in size, right? And if you sum up those enormous, you can just forget the small rectangles because there are few. If your rectangle has less than a little weight, we'll make all this formula. You just forget it. So the total amount of mass that the small tiny rectangles consume anyway is tiny. They're gone, right? And you assume that the guy was giving the right answer. They were all monochromatic. Now you are left with this enormous, the majority of the mass is still left and they are covered by large rectangles, right? Now, suppose it can err, but suppose I say that, like this function that I'm having in mind, well, so far we have proven, like, let's say, we'll soon look at inner product, disjointness, and all these hard functions that we know from deterministic communication complexity. Let's focus on inner product. Suppose now I say that this is, a rather hard function in the sense that not only we proved this volume argument where we showed by linear algebra method that the largest monochromatic rectangle is quite small in size. It's size 2 to the n. So its probability mass under the uniform distribution is 1 over 2 to the n, right? Because the total volume is 2 to the 2n. So it's 1 over 2 to the n. Now suppose I said, forget about monochromatic rectangle. This function is so hard that if you give me any large rectangle, the differences between the number of ones and zeros, this function is much harder than what monochromaticity is capturing, but it's got if you have a rectangle and if you look at a random function, what would a random function do? A random function would put, if this rectangle was voluminous, large in size, every point is being colored by 0 or 1, right? With probability half. So by just Chernow bound or whatever, you will know that in this enormous thing, mostly half of these are colored 0 and half of these are colored 1s, right? Which is being as far as you can be from monochromaticity, right? It's not that it missed monochromaticity by a few points, but it just completely missed one. It's completely confused. The rectangle is basically the rectangle's view is, oh, this is like a random function. What it has isolated is like came from some random darts being thrown and they were all equally likely being 0 or 1, right? Now, if I say inner product has this pseudo-random property that on large rectangles, it appears, oh, although it's a very special function inner product coloring with the points, but to the large rectangle it appears completely mixed. In fact, this was the point of Choor and Goldreich for randomness extractors, that in a large rectangle it will look completely mixed. Yeah, not only will it not be monochromatic, it will be totally mixed. Yeah, the total number of ones minus the total number of zeros will be a very small number. Yeah, then we are in good shape, right? Because these large rectangles, whenever either a rectangle is very small or a rectangle is large. If a rectangle is large, anyway, our deterministic protocol labeled it one way or the other, but it doesn't matter. Whichever way it labeled, half the time it's wrong. So that if you sum it up, you're going to this enormous mass that it is covering, half of that is erroneous, right? And you're done. This is the crux of the discrepancy method, right? That a function which has small discrepancy, right? I mean, it also appears in graph coloring if you're doing the. I mean, anyway, so this is like you're coloring the Boolean cube. A Boolean function is basically two coloring the Boolean cube. And you want to say that the discrepancy of this coloring is extremely small with respect to rectangles. Yeah, it's just looking like a random thing. Okay, so let me define this, all that I said, in the formal way. So discrepancy under mu of a rectangle R, yeah, for a function f is exactly what I just said, which is like probability, yeah, when you sample according to mu, yeah, f of x y is equal to 0 and xy is in R minus the probability if xy equal to 1 and xy is in R. Yeah, the absolute, so it's a non-negative number, so you just take the absolute value of this difference, right? Okay. Now notice that if the rectangle was monochromatic, then the discrepancy would be just the mu mass of this rectangle, right? Because it'll always be of one color, right? But here the rectangle need not be monochromatic. So basically, you're just summing up, this, you can think of this as also saying, mu of R intersected with F inverse of 0 minus mu of R intersected with F inverse of 1. Right? Just the same thing. Is this clear? This is the definition. Yeah. This is a definition of discrepancy. Yeah. Sorry, this is a definition of the discrepancy of a given rectangle. Okay. Now discrepancy mu of f would be defined as the maximum over all rectangles. Yeah. Just as before, when we were looking at the volume, yeah, we were going through all possible rectangles and we were trying to maximize the volume. Here as well, we are going to say maximize over all rectangle and discrepancy mu R of it. Right? So R is a rectangle. And you can also define discrepancy of f to be the minimum over all mu, because the smaller the discrepancy, the more random the function is, the harder the function is, right? A random function with high probability will have very small discrepancy, right? Because it's going to be equidistributed. So, in fact, that's a calculation you should do as part of your assignment to show that a random function has very small discrepancy. So, minimum over mu and yeah, discrepancy mu r of it. So, this is a min max. Yeah. Okay. Is this clear, the definition? Now, why is this good? I mean, this actually the proof I've just told you in English, right? I mean, you just write it out mathematically and it just forms a proof. So here's the discrepancy method, which is the following. I want to say that, you know, if I have randomized half minus epsilon of f, yeah, is greater than discrepancy. Sorry, not this. D mu half minus epsilon of f. Yeah, for every mu that we saw, this is the easy side of Yao. So far, this is just Yao, and here's the thing that we need, which is equal to log of 2 epsilon divided by discrepancy mu of f. So if discrepancy mu of f is very small, it's appearing in the denominator, so you get a large quantity there. Yeah, 2 epsilon is, now this is very powerful. You see, for instance, if discrepancy mu of f is like, let's assume 1 over 2 to the n. Yeah, it can never be smaller than that. Yeah, roughly. So it's 1 over 2 to the n. Then epsilon can be pretty small, right? As long as epsilon is, say epsilon is like 1 over 2 to the n by 3. So that means, you know, you are trying to, so let's see, say epsilon is equal to 1 over 2 to the n by 3, and discrepancy mu of f is 1 over 2 to the n by 2. These numbers are not just random, we will prove for a specific function. Yeah, suppose this is the case. So that means, you know, even if you want to err with probability really close to half minus 1 over 2 to the n by 3, you require omega n bits of communication. Right? Yeah. You agree, right? I mean, this is, I mean, if provided this is true. Right? Provided this is true, this implies that, right? Okay. And why is this true? This is true because of exactly just converting into algebra the thing I just said. Yeah. Because suppose take any such protocol. So we're going to prove this, right? So take any protocol, deterministic protocol. It's let's say of course C. So let pi. So proof is just very simple. Let pi be a deterministic protocol of course C. In fact, all that we are going to use about pi is that it's a partition into 2 to the C rectangles of the input space, not monochromatic, but rectangles, right? Now, pi is erring with probability at the most half minus epsilon, so it's giving me the right answer with probability at least half plus epsilon. So probability of when I sample, you know, xy according to mu, f of xy is equal to pi of xy. Yeah, what is the difference between this and that, and when it's erring? Yeah, this is greater than equal to 2 epsilon, right? So this gap, there's a substantial gap on the right answers, and discrepancy is saying within a rectangle, the gap cannot be too large. So there's a tension. right? So the protocol is doing on the whole, on the global scale, it is doing 2 epsilon apart. The discrepancy is saying, but it's breaking up inputs into chunks of rectangles. Within a rectangle, the discrepancy is saying, oh, you're very tiny, the gap. So you got to have many rectangles for the gap to accumulate, right? That's the whole thing. So now there are 2 to the C leaves. So I can just say that this is therefore 2 epsilon is going to be greater than equal to, yeah. The probable, okay, I'm going to sum from for each leaf, L in leaf of pi, yeah. And if I just take, the using, what is it called? When you
Natural.
triangle inequality. Yeah. And so probability of x, y, sorry, probability of mu f of x, y equals 0 minus, and let me just write it this way. Okay. And x, y is in RL. F of x, y equals 0. Sorry, 1, and x, y is in RL. Yeah, this is my triangle inequality. I just pushed in the absolute value inside, right? Well,
Change this.
huh?
Change this side. 12 side is this time. You want left right hand side to be greater.
I want right hand side to be greater than equal to. Oh, right. Yeah, of course. Yeah. Yeah, and otherwise I would not be able to push the inside also. Very good. Yeah. And I do want that. Yeah, because this is the left hand side is an upper bound of this gap. Yeah, so that upper bound better be greater than what it actually is, which is at least 2 epsilon. Yeah. So now, well, because this RL, you understand what I mean by this RL, right? The RL is the rectangle corresponding to the leaf L, right? Now, this is an arbitrary rectangle. So here I can apply, this is at most discrepancy, right? So therefore I'm done, right? Basically now I get that 2 to the C, this implies that 2 to the C into discrepancy of mu of f. Yeah, because this thing is exactly discrepancy mu R L of f. Yeah, and which is at most discrepancy mu of f, right? So this is greater than equal to epsilon, and therefore C is greater than equal to log 2 epsilon log 2 epsilon by, which is exactly what we want to prove. Yeah. So this is anyway just what I just said. Yeah, I mean you're just summing over these rectangles, and in each rectangle you are accumulating, like, because why did it happen this way? Because every leaf is labeled by one way or the other. It has to declare the entire leaf, entire set of inputs. This is the weakness of a deterministic protocol, right? It has to tell me exactly in a leaf, what am I going to call it, 0 or 1? Whichever way it calls it gets trapped because of discrepancy. Okay? So, right. Okay. That sounds good, but what good is this measure? How do you prove such things, right? Yeah, how do you prove for an explicit function? Yeah, it's not hard to show this for a random function just by the first moment. Yeah, but again, if you want to give me an explicit function, how do you show that this discrepancy? Yeah, and as I said, the inner product function is like a pseudo random function. It behaves it can fool rectangles. Yeah, as if it's a completely random. Yeah, and, yeah, this phenomena is known in many communities, as I said. There's this notion that there's this DNS Chung, the graph theorist Chung, called it some phenomena about graphs. Chor and Goldreich called it the two-source extractor. In communication complexity, we call it the discrepancy is small. But it's basically, like it's the same phenomena being just very nice linear algebraic property being used. again and again and rediscovered even now in many different forms. Okay, so let's prove this. Yeah. Now I'll give you actually three proofs of this because this is one of my favorite theorems, and there's a lot to learn from, I think, from each proof. Yeah. In every proof, there is this Cauchy-Schwarz, which will do an amazing thing. Yeah. In every one of those proofs, but I believe each proof is applying Cauchy-Schwarz slightly different. Okay. So let's look at first. I'll look at a linear algebraic proof, completely linear algebra. Some people call it Lindsay's lemma. I don't know, but it will just follow from just a spectral analysis. And I'll start with that because that's in some sense the most obvious thing. Yeah, because inner product, after all, is defined very algebraically, right? It's an inner product modulo 2. So if you think of this, this is our inner product. And by the way, an important thing is, a simple but important thing is, I can write discrepancy mu of f. Yeah, when I want to write it, I may assume that f is 1 minus 1 value, because then it just becomes a sum, right? It's a sum over what? So let's call it the rectangle R. So if I want to upper bound the discrepancy with respect to a given distribution, I need to upper bound for every rectangle because it's maximized over all possible rectangles, right? So I'm just defining this discrepancy mu R of f. What is this? This is, R of f. R is a rectangle. That means I can always write it as some characteristic function of the row x times some characteristic function of the y's, right? This is a 0, 1 value characteristic function, right? So it's like it's some subset A cross B. R is A cross B. A is a subset of the rows. It's a submatrix, right? A is a subset of the rows. B is a subset of the columns. So A of x is the corresponding 0, 1 value function, and B is the corresponding 0, 1 value function. Yeah. So if you are not in B, then you output 0. This is a standard thing. So A of x times B of y, right? This is a nice, A is just a function of, so I can rewrite this as the absolute value of A of x times B of y, right? Times, yeah, well, I mean, you may call it minus 1 to the f of xy, yeah, which is like 1 minus 1 value, which is exactly what, and x and y are being sampled, sorry, let's call it the expectation of this x and y being sampled according to me. This is exactly what discrepancy is, right? Because if I do this minus 1, anyway, this plus minus automatically appears. Okay. Right? So now what I'm going to show is I'm going to consider the uniform for inner product. I'm going to consider the uniform distribution. Yeah, because inner product, as I said, behaves like a random function under the uniform distribution Fools thing. So let's look at the uniform distribution. That means every point has got 1 over 2 to the 2n probability mass. Every xy. Yeah. Okay. Now, so if look at the matrix of inner product, this is basically a Hadamard matrix, right? H of n. It's a Hadamard matrix in the sense that if all these entries are 1 minus 1 value. Yeah. Yeah, I mean 0 has become 1, 1 has become minus 1, and now it's a unitary matrix, right? I mean, because, well, it's not unitary, it's an orthogonal matrix, it's not normalized. If I normalize it, it becomes unitary. So if you take the inner product, the scalar product of any two of the rows or any two of the columns, it's going to be exactly 0. Yeah, because the encoding here is like a linear form. Yeah, you can think of each row as a linear form and each column is a point, and you're evaluating a linear form over a point. Yeah, this is what minus 1 to the x dot y is doing. So, right. So here for inner product, yeah, I mean inner product of xy, I'm not defining it as minus 1 to the inner product of xy, right? So X defines a linear form. Yeah, this is like two lives, right? And if your quantum X is a bra and Y is like ket, so this is like a linear form. X is like a linear form looking for a point to evaluate. And so, when you look at this row X, yeah, that's a linear form and it's evaluating in all 2 to the n points and either 1 to minus 1. Exactly half of them would be 1 and exactly half of them would be minus 1. Not just that, but any two linear forms are orthogonal, right? So if you take the linear product of them, this will sum up to 0. Okay? Is this clear? Yeah, so this is the standard property of this thing. Yeah? So this is a orthogonal matrix. Not unitary because it's not normalized, but it's an orthogonal matrix. Yeah. Okay. So this quantity, this thing is just under the, because I'm under the uniform distribution, yeah, this I'm calling Hn, yeah, this matrix, it's nothing but, let's say, this A is now a vector, so let's say R is equal to A cross B, so it's nothing but A dot Hn dot B, right? Divided by 2 to the 2n. Do you agree? I've just changed it to matrix notation. This is matrix, sorry, this dot is just matrix multiplication. Yeah. There's no, that's all I mean. Like, you're because Hn times B, so B is a column vector, right? So this is a column vector, and this is a row vector. Yeah, so the column vector, I mean, you're only multiplying things which are both in A. So this column vector, this is a 1, 0, this is a column vector characteristic vector, right? Yeah, so it's picking out only those things which lie in the columns that correspond to B. Otherwise, it's 0. So those entries will not be multiplied. And A from this side, it's a row vector. So it's only picking out those rows of H which want to be which are in the set A. So this is exactly that, right? And you are taking an absolute value divided by, because I need to do this expectation because I'm taking the uniform distribution. Yeah. So this is just now here's the first application of the Cauchy-Schwarz, right? So this is less than equal to the length of this vector. This is a vector after all, right? And now this is arithmetic multiplication times the length of H and B by 2 to B. Yeah, this is Cauchy-Schwarz. Yeah. Okay. Now let's do a bit of linear algebra, just one line, right? So for any matrix, this is, I claim this H of n times B, this length, is always at most the operator norm of H of n times the length of B. Yeah, because how is the operator norm defined? The operator norm is defined in this way. Yeah, I mean, this should be easy. The operator norm of any matrix H of n is defined to be maximum over all V, such that the length of V is equal to 1. You do this in the
Not in this name, I thought it's the largest eigenvalue now.
yeah, which is the operator norm is the largest eigenvalue.
Yeah, I don't introduce this name.
Yeah. Okay, so this is max over V, H of V. Length of H of V. Okay. This is what the operator norm of matrix is, right? Okay. Now, notice that, so if I can bound the operator, okay, let's just say before that, so this is equal to or less than equal to, okay, so what is the length of A? The length of A is, well, A can be, if A was all ones, then you would have 2 to the n entries. So this is the Euclidean length, right? You're summing up. So this is at most square root of 2 to the n times, therefore, by this the definition of the operator norm, this is the length of the operator norm, sorry, the operator norm times another square root of 2 to the n divided by 2 to the 2. Right? So it now just boils down, this discrepancy calculation boils down to understanding the operator norm of H of n, right? And because it's an orthogonal matrix, the understanding the operator norm is very easy, because now if you look at Hn transpose Hn, this is exactly the identity matrix on 2 to the n entries, right? Sorry, not the identity matrix, but it's not orthogonal, sorry, it's not unitary, a scalar, right? So it's like 2 to the n times the identity matrix. Yeah. So therefore, the operator norm is going to be 2 to the n by 2 square root of this, because the eigenvalues get squared, right? It turns out, not always, but here the H of n is a symmetric matrix, so it has real eigenvalues themselves. Yeah, so H of n transpose times H of n, that has only eigenvalue 2 to the n. So the largest eigenvalue for H of n is square root of 2 to the n, which is 2 to the n by 2, right? So therefore, this implies that the operator norm of H of n is exactly equal to 2 to the square root of 2 to the n, right? And so if I just substitute here, this will become, well, square root of 2 to the n times square root of 2 to the n times square root of 2 to the n divided by 2 to the 2n, which is equal to 2 to the minus n by 2. Yeah. So that's it, right? So the discrepancy is 2 to the minus n by 2. It's really small. It's exponentially small again. Yeah. And so hence what we have proven is discrepancy under the uniform distribution for inner product of n is at most 2 to the minus n by 2. Yeah, this is exactly Goldreich argument. Okay. And now if you have this, as I said, this means that if you apply this to our discrepancy method, it means even if you make like really small, massive error, right? You're basically erring almost half the times, half minus, something like 1 over 2 to the n by 3. Those numbers, that is why I chose. Yeah. So you were like really close to half. You're exponentially approaching half error. Even then you would need omega n communication, right? N by 2 minus n by 3, n by 6. Yeah, so this is a very strong bound. So inner product in this sense, as we will see, is much harder than set disjoints. It's harder than almost any explicit function that we know of. Yeah, because it behaves like a random function with respect to rectangles. Okay. For random functions, you can show that the discrepancy would be 2 to the minus n plus little o. So not even n by 2, it's almost behaving like that. For a random function, yeah, discrepancy uniform over f, yeah, is almost equal to 2 to the minus n plus little o of n, yeah, and with high probability, of course. Okay. Now let me show you another proof which will not use linear algebra. Okay, yeah, it will use a little bit of exponent. This will also give you to the various things that has happened to communication complexity. It will use very elementary exponential sums. Okay, very elementary. Okay, and but it's a beautiful proof. This proof is due to Babai-Nissan Szegedi, the one that I will now show you. And it's good to know this proof, because this proof, a large part of it is very widely applicable, because the one that I showed you only will apply when you have spectral norm small. Yeah, but this one will not talk about spectral norm explicitly. Okay, so the starting point is discrepancy uniform of inner product, yeah, or for that matter, any function f. Let's be a little bit general as long as we can. Yeah, is exactly defined to be the expectation over xy, a of x, b of y, and f of xy. Now here I'm assuming f of xy is a 1 minus 1 valued function. Yeah, this is important. Yeah. Now, yeah, a and b are 0, 1 valued functions. So r of xy is now is.
No, there should be some quantification over here.
Oh, right. Oh, okay. Yeah. Thanks. Yeah, okay, right. So now, okay, so now the first step is because I'm taking the absolute value, again, triangle inequality. Yeah, it's like, it looks like they're being very sloppy here, but it's remarkable that this proof works, right? So you do expectation over x, yeah, and you push in this, so this becomes absolute value of a of x times expectation over y, b of y, f of x y. Right? Yeah, I'm just pushing in the absolute value. So this is, sorry, this is less than equal. Yeah, not equal to, but less than equal to.
What is the distribution?
Oh, the distribution here is, let's say, this is some distribution. This will turn out to be the uniform and uniform, but this could be as long as x and y are independent. Yeah, I could do this also y conditioned on, distribution condition on x, but here they are independent. So I'm just pushing it inside, right? So now, then this is even more alarming, is like, okay, now absolute value of a of x is at most 1, right? It's most of the time 0. Notice this, so he's just saying, therefore, this is less than equal to expectation of uniform and expectation. I just drop the a of x, it just disappears. Now, in other words, he has assumed a of a is the largest vector. This is exactly what we did in the linear algebraic calculation, right? We said, oh, a could be arbitrary, and then we applied Cauchy-Schwarz and assumed, oh, therefore the length of a can get most, yeah, which is the same here because he's assumed that a is 1 everywhere, and that's the worst case, right? Okay. Now, here's the thing that is the prelude to the Cauchy-Schwarz. So far, it doesn't look how to look. So square both sides, right? So the left hand side square. So if I do left hand side square, this becomes a square. The right hand side is also now square. But now I can say that this is less than equal to, and this is Cauchy-Schwarz. Whole square, right? Here I've used the value that expectation of z whole square is less than equal to expectation of z square. Yeah, this is same Cauchy-Schwarz with the expectation sign in action. Yeah. And now you just rearrange, so the absolute value is gone, and you just rearrange this thing. So this is a trick worth knowing. So you're introducing 2 copies of y, right? This is like pairwise stuff because you squared it. So that means this is like expectation of x in the uniform distribution, and I may say y1 chosen according to the uniform, y2 chosen according to the uniform, and then by1 times by2 times f of xy1, sorry, the subscript superscripts going up, 1, 2, 1, f of xy2, yeah, and that's it, right? There are just 2 copies because there's 2 independent expectations. You're looking up all possible pairs, yeah. And well, when there is a sum, you just change the order of the sum, right? What else can you do? Hope that things work out. Yeah, so this is less than equal to, now I just push this expectation over here. Sorry. Some magic will happen now, the fun part. Here is subscript. Yeah. So far, I have not assumed anything specific to the functions, right? Just simple algebraic manipulation. Yeah. So now I can drop this. And again, I'm assuming when I'm dropping this, this is also what the Cauchy-Schwarz trick in the linear algebra method did. Yeah. So the linear algebra method did what it did was basically it said that, let's assume B was the all one vector. So therefore, I'm going to do that and just say therefore this is the expectation of y1 uniform, y2 uniform, and just this expectation over x, f of x, y1, f of x, y2. Right? So far, nothing about the inner product. Now, at some point I have to use inner product. This is the first place I believe. So I need to now say, use inner product. And this is a bit like exactly using the orthogonal. It's not just it's not quite an eigenvalue analysis, but it's not. Now I'm going to use the orthogonality of the rows, or the row. Yeah, something over. Yeah, the rows of inner product. Right. So y1 and y2. Sorry, or maybe the columns. Sorry, the columns of the inner product. So y1 and y2 are two columns of the matrix, right? And now you're taking the expectation. So you're looking at the correlation of two columns. Here are the two columns. Yeah. Y1, Y2. And you're taking the correlation, it's basically just the inner product, right? We normalized. Yeah, because you want
Just f of x, y1 plus y2.
Yeah, and so this will basically be 0. Yeah, this is exactly, yeah, this will basically be 0 as long as y1 and y2 are different. Yeah, so the only time it won't be 0 is when y1 and y2 are the same, because they are orthogonal.
No, but I'm saying if you write it as -1.
Yes, yes, yeah, I can do that also. I can do that. Let me do that. No, I was saying this because just to relate to, yeah, correct, but let me just do the expectation of x -1 to the, as Raghu was saying, this is x, y1, XOR y2. Right? This is just the inner product, mod 2, so this becomes this. And what he was saying was that if y1 is not equal to y2, yeah, this is a non-zero quantity. It's a non-zero linear form, and therefore it will completely, the expectation will completely, it's a balanced function on x. Yeah, this is a proof that two columns or two rows are orthogonal. Yeah, which I was alluding to at the beginning. Yeah, and so therefore the only time this will not happen is when y1 and y2 are exactly the same, but you're choosing y1 and y2 at random. The probability of them being the same is 1 over 2 to the n. So this is exactly equal to 1 over 2 to the n. And whenever they are equal, this is 1. So it's exactly equal to 1 over 2 to the n. But remember, you squared everything, right? We squared here in order to apply the Cauchy-Schwarz. So the squared quantity is at most 1 over 2 to the n. So therefore the discrepancy, yeah, of R of inner product is at most 1 over 2 to the n, right? Because you have to take a square root. Yeah. So it's a different proof which uses this orthogonality and Cauchy-Schwarz. Yeah. Okay. The last one. Yeah, sorry, I'm not going in, but yeah, it's a little different. Here I didn't have to go into the although the eigenvalue analysis was very similar. It just looked at it just used the fact that the Hadamard matrix is an orthogonal matrix, which is also what we have done here. But we didn't need to use any unproven fact from linear algebra. Yeah, it's a self-contained proof. The other one will also be a self-contained proof. This one, the one that now I'm going to do, I haven't seen it written anywhere, but to me it seems like it's very specialized for inner product. But it's like viewing inner product, in a certain way. Inner product is special. Yeah. So the third argument.
Also, this proof extends to number on 4 elements.
Huh?
This proof extends.
This proof extends to the number, but yeah, this is why DNS. This extends to a more difficult model.
It's spectral mode.
The spectral one, because then you have to do linear algebra of tensors, and we suck at linear algebra of tensors. What is an eigenvalue of a tensor? Even that is not clear. I mean, there are multiple definitions flying around. Yeah, where because this one stayed away from an operator view of a matrix, it just used very simple fact. This is a more flexible proof that extends in other situations. So the third proof is somewhat similar to this one. It will not use matrix theory at all, but it will use a bit of Fourier analysis. Okay, yeah, very simple. Okay, so let me just write it again. The starting point is inner product discrepancy. UR of inner product. Yeah, here I will shamelessly use the fact that it's inner product. It's expectation over xy. Let's say a of x times b of y times. Let me write what Raghu was saying, minus 1 x y, because I want to use the fact that it's inner product very carefully. Yeah. Okay, so we start exactly the same way. The first trick is also very similar in the sense that now we just say this is less than equal to expectation, precisely what we did with, sorry, expectation over y or x, we went there with x, so let's stay here with x. Expectation over x, I drop it as before, and now you get expectation over y, b of y minus 1 to the xy, this thing, right? So this is, I pulled out a of x and again assumed that a of x was the all one vector. I mean, you know, I'm just doing this triangle inequality. So I can drop this guy, a of x, right? This is exactly what BNS did. Now here, I'm going to use a very special thing about inner product. I'm just going to interpret this thing. So b of y is a function, 0, 1 valued function, right? And you are looking at what are you doing this, if you rewrite it, this is exactly expectation of x with just a different change of notation, b of y, and then chi x of y, right? Now here, x is a linear form, and you are looking at the x is like a parity of y, right? That's what you are doing. So this is basically the correlation of b of y as a function with the xth character or parity, right? This by definition, if you've taken a Fourier analysis course, this is exactly what is the
Yeah.
b hat of x. Yeah, the function b is Fourier except Fourier coefficient. This is exactly, but there's an equality, right? So there is this parity basis, right? It's an orthogonal basis. Yeah, it's the same thing as viewing Hadamard matrix in different ways, right? The columns of the Hadamard matrix are orthogonal, so you can think of, you know, expanding the set of all functions from 0, 1 to the n to 0, 1 or even r, right? Using that parity basis, those vectors, right? And when you expand them, because it's a basis, there's a unique coefficient for every possible function. There's a unique coefficient for each of those polynomials, right? Which is what we call, we glorify it by the name Fourier coefficient, but that's exactly what it is, which is obtained by taking this inner product. Yeah, this is the definition of inner product. The inner product space is defined in this way, and this is that coefficient. If you were to take any function like b, expand it in terms of the parities, well, this is exactly the xth Fourier coefficient. Yeah, the xth character will be multiplied by this and summed up. Yeah, okay. And now, therefore, the discrepancy has become at most the sum, the absolute sum of the Fourier characters of the row set. Right? This is what it is. But now, well, as I said, I have so far not used Cauchy-Schwarz. So now I have to use Cauchy-Schwarz, which is what? Which is basically saying this expectation. Now square row says left-hand side square will be further less than expectation of this b hat of x squared, right? And am I missing something? This seems like too good. Oh, no,
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 the
yeah, yeah,
expectation
yeah,
of
this
X
is-
will give you.
this is fine. So this is basically now therefore this is summation over one over two to the n, summation b hat x squared. Right, I mean, I'm just defining the expectation, yeah. Now, what is the sum of the square of the Fourier coefficient? This, if you've done, again, by the orthonormality of the basis, the sum of the squares is exactly equal to the average value of the function. Yeah, so what I'm saying is for every, this is called Parseval.
Some of the squares will,
So sum of the squares of the Fourier coefficient. Yeah,
also some of the squares will.
no, so let me write it. So for every f, yeah, the expectation over x, so in the time domain, f square of x, this is exactly equal to the summation f hat of s square summed over the characters. Yeah, this just follows by orthonormality. Yeah, this is a very useful thing to remember. Yeah, so now therefore, if I apply over here, this summation of b hat square, yeah, this is exactly equal to the expectation over x, b square of x. But that's at most one, because b square of x is one at each point or zero, right? So therefore, this is less than equal to 1 over 2bn. Yeah. And we're done, right? Because so you get, in every case we get the same bound. Yeah. So therefore, discrepancy of uniform over, yeah, inner product. In every case we get the yeah. Yeah, sorry, I'm over time, but yeah, I'll stop there. Yeah, so I just showed you three proofs. One, using linear algebra at the very beginning, yeah, where I still viewed a matrix as an operator. This is important view, right? I mean, it's not to be thrown away. The second point is where I didn't want to view it as an operator. I just got the first principles from the definition. And the third is also basically first principles. It just uses this, I mean, yeah, I mean, it just uses this inner product in a very careful way where, this is very special. This will only happen for the inner product, where this is the sum of the Fourier coefficients. Using these, the definition of inner product being this. Okay. The second proof, as Yogesh was saying, is very useful because the second proof generalizes to this thing called the number on the four-head model, for which we don't know of any other way of proving things. Okay, so yeah, any question? Otherwise, let's stop.